In this video, I want to go over the calculations that we use to determine the pH of a strong acid in solution. And we're going to see that there's a problem when we do this. If you recall, the pH is equal to the negative log of the concentration of hydrogen ions. And strong acids dissociate completely, so we're going to see when we add hydrochloric acid, we generate, if it's 0.1 molar hydrochloric acid, we're going to have 0.1 molar hydrogen ions, so on and so forth. And we also recall from general chemistry that acids have a pH of -7. So if we were to do something like calculate the pH of a 10 to the -10 molar hydrochloric acid solution, and using these concepts from general chemistry, we see that the pH is equal to the negative log of 10 to the -10, and that crunches to a pH of 10. But wait a minute, that's a basic solution, and acids are only supposed to have a pH of below 7. So it looks as if we have added an acid to create a basic solution. So that clearly can't be right. So let's take a closer look now at the information that we know and try to rationalize what's going on. We said that hydrochloric acid dissociates completely into hydrogen ions and chloride ions. We also know that water autoionizes. So water will generate a small amount of hydrogen ions and hydroxide ions, and that equilibrium is called the Kw, which is equal to 10 to the -14. There's also something new that we know, and it's the concept of electroneutrality. The sum of the positive ions that we have in solution always has to equal the sum of the anions. So the cations plus has to equal the anion concentrations in order for the entire solution to remain electrically neutral. We also know the concentration of chloride ions because that is going to be equal to the amount of hydrochloric acid that we add. Since we're controlling how much we add, how much HCl we add, we know the chloride ion concentration. So what we don't know in this particular case is the hydroxide ions concentration. We don't have a clear way of determining that, but we also don't care. So it's going to be a useful tool for us when we start manipulating these equations to get rid of the hydroxide ion algebraically. You'll see what I mean by that in just a minute. What we do want to know is the hydrogen ion concentration. So we've got all of this information, and we need to sort of put it all together in order to figure out what's going on. So here's how we can approach the problem. I've rewritten all of the information that we know here, and we're going to base the solution on the electroneutrality equation. So we're going to start right there. And that then step 2, we're going to substitute the Cl minus for HCl concentration because of that complete dissociation. And then the last thing that we're going to do is get rid of the hydroxide ions by substituting the Kw equation into the electroneutrality equation. When we do that, we get something that looks like this, and you should be able to confirm that before you continue on with this video. So take a minute, pause the video if you need to, and see if you can do the algebra to go from the two tan colored, starting from the electroneutrality equation and getting down to the expression for hydrogen ion concentration. Okay, now that we're here, let's rearrange this equation to solve for Kw, and when we do that, we get something that looks like this. And we can ask ourselves a couple questions. When we haven't added any hydrochloric acid, we want to know what the hydrogen ion concentration is. So if HCl then is 0, we can go ahead and do some number crunching. We get h squared on the left-hand side, take the square root of Kw, and we get 10 to the minus 7 is the molarity of hydrogen ion concentration. And now when we take the negative log of that, we get 7. This is a much better answer than what we were getting previously, because it makes a lot more sense. If we're not going to add any acid, we should get a neutral solution, and that's exactly what we've got. So what if HCl is not 0? Let's go ahead and start adding, start crunching numbers. So this is when we're adding some hydrochloric acid to our water and trying to figure out the hydrogen ion concentration. We see when we plug this in, we get a quadratic equation. So we're going to need to use some of our high school algebra to solve this problem. If you recall, for the quadratic equation, we set the equation equal to 0 and arrange it so we've got an x squared term, an x term, and a term that doesn't contain x. The coefficients before those are a, b, and c. And for our case here, a is equal to 1, b is the negative concentration of HCl. Remember, those signs need to be carried through. And c is going to be negative Kw. In all of this, then x is the hydrogen ion concentration, which is what we're trying to solve for. So let's repeat that information and go ahead and plug it into our quadratic equation, minus b plus or minus square root of b squared minus 4ac all over 2a. And it looks like so once we have plugged in the various variables. I've adjusted for the signs or taken the signs into consideration here. And remember, you do get 2 answers from this equation. It turns out in this particular case that only one of them gives you a positive value for a concentration, so that's the only one that has any physical meaning. So it turns out that it's the HCl plus of the square root term that's going to be useful. So we'll just stick with that one and plug it in to a couple situations and see what we've got. Now, from the very beginning of this experiment or this video, we used 10 to the minus 10 molar HCl. If we plug that into our solution, we get a concentration of hydrogen ions that yields a pH which is just slightly, ever so slightly below a pH of 7. So it is an acidic solution, and this makes a lot more sense than just plugging in 10 to the minus 10 or into our pH equation, that log term. We can continue down to higher and higher concentrations of HCl. When we get to something that is 10 to the minus 4, or that's around 0.1 millimolar, we're now starting to get pHs that make sense if we were to just do the negative log equation and just completely ignore the dissociation of water. And so that's really the point here that we're seeing, is that when we calculate the pH of a strong acid solution, there are several regions when the solution is really, really dilute. Too little HCl has been added to make any difference, and the pH is actually dependent on the autoionization of water. In this sort of middle region here, we need to pay close attention to the quadratic equation, because both hydrochloric acid and the auto dissociation of water are influencing the pH. Once we get to sort of this low but not extremely low concentrations of hydrochloric acid, we can use the simple form of pH is equal to negative log of hydrogen ion concentration added, and we can ignore the autoionization of water. But then we start to see that as we get to high concentrations of hydrochloric acid, things are starting to deviate again. This has nothing to do with anything we've just discussed, and it actually, the answer is activity, but we're not going to talk about that right now because it requires a conversation about ionic strength, and that would be saved for a separate video. So in conclusion, we've got this equation, the pH is equal to the negative log of hydrogen ion concentrations. And while that's true, we have to remember that the hydrogen ion concentration is influenced by not only the amount of added acid, but also the autoionization of water. Sometimes we can ignore that, but when the concentration of the acid added is low, we cannot ignore the autoionization of water. And so when we incorporate both of those concepts, we end up getting a system of equations that requires our use of the quadratic equation. It does give us a useful or an accurate result. Throughout all of this, we introduced a new concept that was useful for us mathematically called electroneutrality, that says the sum of the ions, the cations, has to equal the sum of all of the anions in solution in order for us to remain electrically neutral. So there you have it, solving strong acid equations using the quadratic equation.